This photo shows about 26 rolls of paper piled together. The rolls are different sizes. Figure 2. When you have large amounts of data, you will need to organize it in a way that makes sense. These ballots from an election are rolled together with similar ballots to keep them organized. Credit. Modification of work, Helmand Province, Afghanistan, Aug. 21, 2009. Voting ballots organized and arranged for counting by Afghan presidential election workers at a local school in the Nawad district. By U.S. Marine Corps. Photo by Staff SGT. William Greason / Wikimedia Commons, public domain. Once you have collected data, what will you do with it? Data can be described and presented in many different formats. For example, suppose you are interested in buying a house in a particular area. You may have no clue about the house prices, so you might ask your real estate agent to give you a sample data set of prices. Looking at all the prices in the sample often is overwhelming. A better way might be to look at the median price and the variation of prices. The median and variation are just two ways that you will learn to describe data. Your agent might also provide you with a graph of the data. In this chapter, you will study numerical and graphical ways to describe and display your data. This area of statistics is called descriptive statistics. You will learn how to calculate, and even more importantly, how to interpret these measurements in graphs. A statistical graph is a tool that helps you learn about the shape or distribution of a sample or a population. A graph can be a more effective way of presenting data than a mass of numbers because we can see where data clusters and where there are only a few data values. Newspapers and the internet use graphs to show trends and to enable readers to compare facts and figures quickly. Statisticians often graph data first to get a picture of the data. Then more formal tools may be applied. Some of the types of graphs that are used to summarize and organize data are the dot plot, the bar graph, the histogram, the stem and leaf plot, the frequency polygon, a type of broken line graph, the pie chart, and the box plot. In this chapter, we will briefly look at stem and leaf plots, line graphs, and bar graphs, as well as frequency polygons and time series graphs. Stem and leaf graphs, stem plots, line graphs, and bar graphs. One simple graph, the stem and leaf graph or stem plot, comes from the field of exploratory data analysis. It is a good choice when the data sets are small. To create the plot, divide each observation of data into a stem and a leaf. The leaf consists of a final significant digit. For example, 23 has stem 2 and leaf 3. The number 432 has stem 43 and leaf 2. Likewise, the number 5432 has stem 543 and leaf 2. The decimal 9.3 has stem 9 and leaf 3. Write the stems in a vertical line from smallest to largest. Draw a vertical line to the right of the stems. Then write the leaves in increasing order next to their corresponding stem. Example 2. For Professor Dean's spring pre-calculus class, scores for the first exam were as follows: smallest to largest: 33, 42, 49, 49, 53, 55, 55, 61, 63. 67, 68, 68, 69, 69, 72, 73, 74, 78, 80, 83, 88, 88, 88, 90, 92, 94, 94, 94. 94, 96, 100. Stem leaf 33 4299 5355 61378899 72348 803888 90244446 10-0. Table 2. 1 stem and leaf graph. The stem plot shows that most scores fell in the 60s, 70s, 80s, and 90s. 8 out of the 31 scores, or approximately 26%. 31. Were in the 90s or 100, a fairly high number of as. Triad 2-1. For the Park City basketball team, scores for the last 30 games were as follows: smallest to largest: 32, 32, 33, 34, 38, 40, 42, 42, 43. 44, 46, 47, 47, 48, 48, 48, 49, 50, 50, 51, 52, 52, 52, 53, 54, 56, 57, 57, 60. 61. Construct a stem plot for the data. The stem plot is a quick way to graph data and gives an exact picture of the data. You want to look for an overall pattern and any outliers. An outlier is an observation of data that does not fit the rest of the data. It is sometimes called an extreme value. When you graph an outlier, it will appear not to fit the pattern of the graph. Some outliers are due to mistakes, for example, writing down 50 instead of 500, while others may indicate that something unusual is happening. It takes some background information to explain outliers, so we will cover them in more detail later. Example 2.2. The data are the distances in kilometers from a home to local supermarkets. Create a stem plot using the data 111523252732333335. 384042454547485556656712.3. Problem. Do the data seem to have any concentration of values? No. The leaves are to the right of the decimal. Solution. The value 12, 3 may be an outlier. Values appear to concentrate at 3 and 4 kilometers. Stem leaf. 115 2357 323358 402557 556 657 7 8 9 10 11 12 3. Table 2. Triad 2 2. The following data show the distances in miles from the homes of off-campus statistics students to the college. Create a STEM plot using the data and identify any outliers. 0 5 0 7 1 1 1 2 1 2 1 3 1 3 1 5 1 5 1 7 1 7 1 8 1 9 2 0 2 2 2 5 2 6 2 8 2 8 2 8 3 5 3 8 4 4 4 8 4 9 5 2 5 5 5 7 5 8 8 0. Example 2 3. Problem. A side-by-side stem and leaf plot allows a comparison of the two data sets in two columns. In a side-by-side stem and leaf plot, two sets of leaves share the same stem. The leaves are to the left and the right of the stems. Table 2-3 and Table 2-4 show the ages of presidents at their inauguration and at their death. Construct a side-by-side stem and leaf plot using this data. President age, president age, president age. Washington 57, Lincoln 52, Hoover 54. J. Adams 61A, Johnson 56F. Roosevelt 51, Jefferson 57, Grant 46, Truman 60. Madison 57, Hayes 54, Eisenhower 62. Monroe 58, Garfield 49, Kennedy 43. J.Q. Adams 57, Arthur 51 L, Johnson 55. Jackson 61, Cleveland 47, Nixon 56. Van Buren 54 B, Harrison 55, Ford 61. W.A. Harrison 68, Cleveland 55, Carter 52. Tyler 51, McKinley 54, Reagan 69. Polk 49 T, Roosevelt 42 G, H.W. Bush 64. Taylor 64, Taft 51, Clinton 47. Fillmore 50, Wilson 56 G, W. Bush 54. Pierce 48, Harding 55, Obama 47. Buchanan 65, Coolidge 51. Table 2, 3 presidential ages at inauguration. President age, president age, president age. Washington 67, Lincoln 56, Hoover 90. J. Adams 90A, Johnson 66F. Roosevelt 63. Jefferson 83, Grant 63, Truman 88. Madison 85, Hayes 70, Eisenhower 78. Monroe 73, Garfield 49, Kennedy 46. J.Q. Adams 80, Arthur 56 L, Johnson 64. Jackson 78, Cleveland 71, Nixon 81. Van Buren 79 B, Harrison 67, Ford 93. W.A. Harrison 68, Cleveland 71, Reagan 93. Tyler 71, McKinley 58. Polk 53 T, Roosevelt 60. Taylor 65, Taft 72. Fillmore 74, Wilson 67. Pierce 64, Harding 57. Buchanan 77, Coolidge 60. Table 2, 4 presidential age at death. Solution. Ages at inauguration, ages at death. 9987776324669. 87777666555544444422 11111053666778. 9854442 111060033445677778. 701112347889. 801358. 90033. Table 2. Triad 2-3. The table shows the number of wins and losses the Atlanta Hawks have had in 42 seasons. Create a side-by-side stem and leaf plot of these wins and losses. Losses win season, losses win season. 34-48, 141, 41, 22. 34-48, 239, 43, 23. 46-36, 3, 44, 38, 24. 46-36, 439, 43, 25. 36-46, 525, 57, 26. 47-35, 6, 40, 42, 27. 51-30, 17, 36, 46, 28. 53-29, 8, 26, 56, 29. 51-31, 9, 32, 50, 30. 41-41, 10, 19, 31, 31. 36-46, 11, 54, 28, 32. 32-50, 12, 57, 25, 33. 51-31, 13, 49, 33, 34. 40-42, 14, 47, 35, 35. 39-43, 15, 54, 28, 36. 42-40, 16, 69, 13, 37. 48-34, 17, 56, 26, 38. 32-50, 18, 52, 30, 39. 25-57, 19, 45, 37, 40. 32-50, 20, 35, 47, 41. 30-52, 21, 29, 53, 42. Table 2. Another type of graph that is useful for specific data values is a line graph. In the particular line graph shown in example 2.4, the x-axis, horizontal axis, consists of data values and the y-axis, vertical axis, consists of frequency points. The frequency points are connected using line segments. Example 2.4. In a survey, 40 parents were asked how many times per week a teenager must be reminded to do their chores. The results are shown in Table 2. 7 and in Figure 2, number of times teenager is reminded frequency. 1 5 2 8 3 14 4 7 5 4. Table 2 7. A line graph showing the number of times a teenager needs to be reminded to do chores on the x-axis and frequency on the y-axis. Figure 2. Triad 2 4. In a survey, 40 people were asked how many times per year they had their car in the shop for repairs. The results are shown in Table 2.8. Construct a line graph. Number of times in shop frequency. 7, 110, 214, 39. Table 2a. Bar graphs consist of bars that are separated from each other. The bars can be rectangles or they can be rectangular boxes, used in three-dimensional plots, and they can be vertical or horizontal. The bar graph shown in example 2. 5 has age groups represented on the x-axis and proportions on the y-axis. Example 2.5. Problem. The percentage of US-based TikTok users by age is shown in Table 2.9. Construct a bar graph using these data. Age groups proportion percent of TikTok users. 10-19-32, 5%. 20-29-29, 5%. 30-39-16, 4%. 40-49-13, 9%. 50 plus 7, 1%. Table 2.9. Solution. Bar graph of age groups against percentage of TikTok users. The percentage ranges from 0 to 35 in increments of 5. Bar of age group 10 to 19 has height of 32%, 20 to 29 has height of 29%, 30 to 39 has height of 16%, 40 to 49 has height of 14%, 50 plus has height of 7%. Figure 2.3. Triad 2.5. The population in Park City is made up of children, working-age adults, and retirees. Table 2. 10 shows the three age groups, the number of people in the town from each age group, and the proportion percent of people in each age group. Construct a bar graph showing the proportions. Age groups, number of people, proportion of population. Children 67, 0, 59, 19%. Working age adults 152, 198, 43%. Retirees 131, 662, 38%. Table 2. 10. Example 2.6. Problem. The columns in Table 2. 11 show the projected data for the year 2030 for the number and percentages of high school graduates by geographic region in the United States. Create a bar graph for these data with the geographic region qualitative data on the x-axis and the percentage of high school data quantitative data on the y-axis. Region number of graduates, percentage of graduates. Northeast 517, 720, 16, 1%. Midwest 695, 170, 21. 6%. South 1 253, 540, 39, 0%. West 749, 423, 3%. Table 2. 11. Solution. Bar graph of geographic region against percentage of graduates. Percent of graduates ranges from 0 to 45 in increments of 5. Bar of Northeast has height of 16%, Midwest has height of 22%, South has height of 39%, West has height of 23%. Figure 2.4. Triad 2. Park City is broken down into 6 voting districts. The table shows the percent of the total registered voter population that lives in each district, as well as the percent total of the entire population that lives in each district. Construct a bar graph that shows the registered voter population by district. District registered voter population, overall city population. 115, 5%, 19, 4%. 212, 2%, 15. 6%. 39, 8%, 9, 0%. 417, 4%, 18, 5%. 522, 8%, 20, 7%. 622, 3%, 16, 8%. Table 2. 12. Example 2.7. Problem. Below is a two-way table showing the types of pets owned by men and women. Dogs, cats, fish total. Men 4,228. Women 4,6,212. Total 8,8,420. Table 2. 13. Given these data, calculate the conditional distributions for the subpopulation of men who own each pet type. Solution. Men who own dogs equals 4,8 equals 0. Men who own cats equals 2,8 equals 0, 25. Men who own fish equals 2,8 equals 0, 25. Note, the sum of all of the conditional distributions must equal 1. In this case, 0,5 plus 0,25 plus 0,25 equals 1. Therefore, the solution checks. Try it 2.7. Given the data in Table 2, 13. Calculate the conditional distributions for the subpopulation of women who own each pet type. Histograms, frequency polygons, and time series graphs. For most of the work you do in this book, you will use a histogram to display the data. One advantage of a histogram is that it can readily display large data sets. A rule of thumb is to use a histogram when the data set consists of 100 values or more. A histogram consists of contiguous adjoining boxes. It has both a horizontal axis and a vertical axis. The horizontal axis is labeled with what the data represents, for instance, distance from your home to school. The vertical axis is labeled either frequency or relative frequency or percent frequency or probability. The graph will have the same shape with either label. The histogram, like the stem plot, can give you the shape of the data, the center, and the spread of the data. The relative frequency is equal to the frequency for an observed value of the data divided by the total number of data values in the sample. Remember, frequency is defined as the number of times an answer occurs. If f equals frequency n equals total number of data values, or the sum of the individual frequencies, and rf equals relative frequency, then rf equals fn. For example, if 3 students in an English class of 40 students received from 90% to 100%, then f equals 3, n equals 40, and rf equals fn equals 340 equals 0. 75% of the students received 90-100%. 90-100% are quantitative measures. To construct a histogram, first decide how many bars or intervals, also called classes, represent the data. Many histograms consist of 5 to 15 bars or classes for clarity. The number of bars needs to be chosen. Choose a starting point for the first interval to be less than the smallest data value. A convenient starting point is a lower value carried out to one more decimal place than the value with the most decimal places. For example, if the value with the most decimal places is 6. 1 and this is the smallest value, a convenient starting point is 656105 equals 65. We say that 65 has more precision. If the value with the most decimal places is 223 and the lowest value is 15, a convenient starting point is 1495. 1505 equals 1. 495. If the value with the most decimal places is 3234 and the lowest value is 10, a convenient starting point is 09995 100. 5 equals 09995. If all the data happen to be integers and the smallest value is 2, then a convenient starting point is 15205 equals 15. Also, when the starting point and other boundaries are carried to one additional decimal place, no data value will fall on a boundary. The next 2 examples go into detail about how to construct a histogram using continuous data and how to create a histogram using discrete data. Example 2, 8. The following data are the heights in inches to the nearest half inch of 100 male semi-professional soccer players. The heights are continuous data since height is measured. 60, 65, 61. 61, 61, 5, 63. 5, 63, 5, 63. 564 64 64 64 64 64 64 64 5 64 5 64 5 64 5 64 5 64 5 64 5 64 566 66 66 66 66 66 66 66 66 66 66, 5, 66, 5, 66, 5, 66, 5, 66, 5, 66, 5, 66, 5, 66, 5, 66, 5, 66, 5, 66, 5, 67, 67. 67, 67, 67, 67, 67, 67, 67, 67, 67, 67, 67, 5, 67, 5, 67, 5, 67, 5, 67. 5, 67, 5, 67. 568, 68, 69, 69, 69, 69, 69, 69, 69, 69, 69, 69, 69, 5, 69. 569, 5, 69, 5, 69. 570, 70, 70, 70, 70, 70, 75, 75, 75, 71, 71, 71, 72, 72, 72. 72, 5, 72, 5, 73, 73. 574. The smallest data value is 60. Since the data with the most decimal places has one decimal, for instance 61. 5. We want our starting point to have 2 decimal places. Since the numbers 05050, 5, etc. are convenient numbers, use 0. 5 and subtract it from 60, the smallest value, for the convenient starting point. 6005 equals 5995, which is more precise than, say, 615 by 1 decimal place. The starting point is then 5995. The largest value is 74, so 74 plus 05 equals 74. 5 is the ending value. Next, calculate the width of each bar or class interval. To calculate this width, subtract the starting point from the ending value and divide by the number of bars. You must choose the number of bars you desire. Suppose you choose 8 bars, 74, 0, 5 minus 59, 95 equals 14, 114. 1 divided by 8 equals 1. 76. Note we will round up to 2 and make each bar or class interval 2 units wide. Rounding up to 2 is one way to prevent a value from falling on a boundary. Rounding to the next number is often necessary even if it goes against the standard rules of rounding. For this example, using 176 as the width would also work. A guideline that is followed by some for the width of a bar or class interval is to take the square root of the number of data values and then round to the nearest whole number if necessary. For example, if there are 150 values of data, take the square root of 150 and round to 12 bars or intervals. The boundaries are 59, 95, 59. 95 plus 2 equals 61, 95 61, 95 plus 2 equals 63, 95 63, 95 plus 2 equals 65, 95 65. 95 plus 2 equals 67, 95 67, 95 plus 2 equals 69, 95 69, 95 plus 2 equals 71, 95 71. 95 plus 2 equals 73, 95 73, 95 plus 2 equals 75, 95 the heights 60 through 61, 5 inches are in the interval 59, 95 61. 95, the heights that are 63, 5 are in the interval 61, 95 63 95, the heights that are 64 through 64, 5 are in the interval 63, 95 65. 95, the heights 66 through 67, 5 are in the interval 65, 95 67 95, the heights 68 through 69, 5 are in the interval 67, 95 69. 95, the heights 70 through 71 are in the interval 69, 95 71 95, the heights 72 through 73, 5 are in the interval 71, 95 73. 95, the height 74 is in the interval 73, 95 75 95. The following histogram displays the heights on the x-axis and relative frequency on the y-axis. Histogram consists of 8 bars with the y-axis in increments of 0, 5 from 004 and the x-axis in intervals of 2 from 59 95 75 95. Figure 2. 5 try it 2. 8 The following data are the shoe sizes of 50 male students. The sizes are continuous data since shoe size is measured. Construct a histogram and calculate the width of each bar or class interval. Suppose you choose 6 bars. 9 9 9 5 9 5 10 10 10 10 10 10 10 5 10 5 10 5 10 5 10 5 10 5 10 5 10 5 11 11 11 11 11 11 11 11 11 11 11 11 11 11 5 11 5 11 5 11 5 11 5 11 5 11 5 12 12 12 12 12 12 12 12 5 12 5 12 5 12 5. 14 Example 2. 9 Create a histogram for the following data. The number of books bought by 50 part-time college students at ABC College. The number of books is discrete data since books are counted. 1 1 1. 1 1 1 1 1 1 1 1 2 2 2 2 2 2 2 2 2 2 3 3 3 3 3 3 3 3 3 3 3 3 3 3 3 3 4 4 4 4 4 4 5 5 5 5. 5 6 6 11 students buy 1 book, 10 students buy 2 books, 16 students buy 3 books, 6 students buy 4 books, 5 students buy 5 books, 2 students buy 6 books. Because the data are integers, subtract 0.5 from 1, the smallest data value, and add 0.5 to 6, the largest data value. Then the starting point is 0.5 and the ending value is 6.5. Problem next, calculate the width of each bar or class interval. If the data are discrete and there are not too many different values, a width that places the data values in the middle of the bar or class interval is the most convenient. Since the data consist of the numbers 1, 2, 3, 4, 5, 6, and the starting point is 0.5, a width of 1 places the 1 in the middle of the interval from 0.5 to 1. 5's the 2 in the middle of the interval from 1.5 to 2.5, the 3 in the middle of the interval from 2.5 to 3.5, the 4 in the middle of the interval from 2, the 5 in the middle of the interval from 2, and the in the middle of the interval from 2. Solution 3.5 to 4.5, 4.5 to 5.5, 6.5 to 6.5. Calculate the number of bars as follows. 6.5 minus 0. 5 equals 6. 6 divided by 1 equals 6, where 1 is the width of a bar. Therefore, bars equals 6. The following histogram displays the number of books on the x-axis and the frequency on the y-axis. Histogram consists of 6 bars with the y-axis in increments of 2 from 0.16 and the x-axis in intervals of 1 from 0. 5 6 5 Figure 2. 6 Try it 2. 9. The following data are the number of sports played by 50 student athletes. The number of sports is discrete data since sports are counted. 1 1 1 1 1 1 1. 1 1 1 1 1 1 1 1 1 1 1 1 1 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 3 3 3 3 3 3 3. 320 student athletes play one sport. 22 student athletes play two sports. 8 student athletes play three sports. Fill in the blanks for the following sentence. Since the data consist of the numbers 1, 2, 3, and the starting point is 0, 5, a width of 1 places the 1 in the middle of the interval 0, 5, 2, the 2 in the middle of the interval from 2, and the 3 in the middle of the interval from 2. Example 210 problem using this data set, construct a histogram. Number of hours my classmates spent playing video games on weekends 9. 95 10 2, 25 16, 75 0 19. 522, 575 15 12, 75 5 5 11 10 20, 75 17, 5 23 21, 9 24 23, 75 18 20 15 22. 9 18 8 20, 5 table 2, 14 solution. This is a histogram that matches the supplied data. The x-axis consists of 5 bars in intervals of 5 from 0 to 25. The y-axis is marked in increments of 1 from 0 to 10. The x-axis shows the number of hours spent playing video games on the weekends, and the y-axis shows the number of students. Figure 2. 7. Some values in this data set fall on boundaries for the class intervals. A value is counted in a class interval if it falls on the left boundary, but not if it falls on the right boundary. Different researchers may set up histograms for the same data in different ways. There is more than one correct way to set up a histogram. Try it too. 10. The following data represent the number of employees at various restaurants in New York City. Using this data, create a histogram. 22, 35, 15, 26, 40, 28, 18, 20, 25, 34, 39, 42, 24, 22, 19, 27, 22. 34, 40, 20, 38, and 28. Use 10, 19 as the first interval. Collaborative exercise. Count the money bills and change in your pocket or purse. Your instructor will record the amounts. As a class, construct a histogram displaying the data. Discuss how many intervals you think is appropriate. You may want to experiment with the number of intervals. Frequency polygons. Frequency polygons are analogous to line graphs, and just as line graphs make continuous data visually easy to interpret, so too do frequency polygons. To construct a frequency polygon, first examine the data and decide on the number of intervals or class intervals to use on the x-axis and y-axis. After choosing the appropriate ranges, begin plotting the data points. After all the points are plotted, draw line segments to connect them. Example 2. 11. A frequency polygon was constructed from the frequency table below. Frequency distribution for calculus final test scores lower bound upper bound frequency cumulative frequency 49, 559, 55 559, 569, 510 1569. 579, 530 40 579, 589, 540 85 89, 599, 515 100. Table 2. 15. A frequency polygon was constructed from the frequency table below. Figure 2. 8. The first label on the x-axis is 44, 5. This represents an interval extending from 39, 5 to 49, 5. Since the lowest test score is 54, 5, this interval is used only to allow the graph to touch the x-axis. The point labeled 54, 5 represents the next interval or the first real interval from the table and contains 5 scores. This reasoning is followed for each of the remaining intervals with the point 104, 5 representing the interval from 99, 5 to 109, 5. Again, this interval contains no data and is only used so that the graph will touch the x-axis. Looking at the graph, we say that this distribution is skewed because one side of the graph does not mirror the other side. Try it too. 11. Construct a frequency polygon of U.S. presidents, ages at inauguration shown in Table 216. Age at inauguration frequency 41, 546, 5446, 551. 51151, 556, 51456, 561, 5961, 566, 5466, 571, 52. Table 2. 16. Frequency polygons are useful for comparing distributions. This is achieved by overlaying the frequency polygons drawn for different data sets. Example 2. 12. We will construct an overlay frequency polygon comparing the scores from example 211 with the student's final numeric grade. Frequency distribution for calculus final test scores, lower bound, upper bound frequency, cumulative frequency 49. 559, 555 559, 569, 510 1569, 579, 530 40 579, 589, 540 80 589, 599. 515 100 Table 217 Frequency distribution for calculus final grades lower bound upper bound frequency cumulative frequency 49, 559, 510 1059, 569, 510 2069, 579, 530 5079, 589, 540 595 89, 599, 55 100 Table 2. 18 This is an overlay frequency polygon that matches the supplied data. The x-axis shows the grades and the y-axis shows the frequency. Figure 2, 9 Try it 2. 12 We will construct an overlay frequency polygon comparing the scores from example 212 with the student's final test scores in algebra. Frequency distribution for algebra final test scores lower bound upper bound frequency cumulative frequency 49. 559, 510 1059, 569, 55 15 69, 579, 540 55 79, 589, 530 590 89, 599. 510 100 Table 2. 19 Constructing a time series graph. Suppose that we want to study the temperature range of a region for an entire month. Every day at noon we note the temperature and write this down in a log. A variety of statistical studies could be done with these data. We could find the mean or the median temperature for the month. We could construct a histogram displaying the number of days that temperatures reach a certain range of values. However, all of these methods ignore a portion of the data that we have collected. One feature of the data that we may want to consider is that of time. Since each date is paired with the temperature reading for the day, we don't have to think of the data as being random. We can instead use the times given to impose a chronological order on the data. A graph that recognizes this ordering and displays the changing temperature as the month progresses is called a time series graph. To construct a time series graph, we must look at both pieces of our paired data set. We start with a standard Cartesian coordinate system. The horizontal axis is used to plot the date or time increments, and the vertical axis is used to plot the values of the variable that we are measuring. By doing this, we make each point on the graph correspond to a date and a measured quantity. The points on the graph are typically connected by straight lines in the order in which they occur. Example 2. 13 Problem The following data shows the annual consumer price index, each month, for 10 years. Construct a time series graph for the annual consumer price index data only. Year Jan Feb Mar April May June Jul 1 181, 7 183, 1 184, 2 183, 8 183, 5 183, 7 183, 9 2 185, 2 186, 2 187, 4 188, 0 189, 1 189, 7 189, 4 3 190, 7 191, 8 193, 3 194, 6 194, 4 194, 5 195, 4 4 198, 3 198, 7 199, 8 201, 5 202, 5 202, 9 203. 5 202, 416 203, 499 205, 352 206, 686 207, 949 208, 352 208, 299 6 211, 80 211, 693 213, 528 214, 823 216, 632 218, 815 219, 964 7 211, 143 212, 193 212, 709 213, 240 213, 856 215, 693 215, 351 8 216, 687 216, 741 217, 631 218, 9 218, 178 217, 965 218, 11 9 220, 223 221, 309 223, 467 224, 906 225, 964 225, 722 225, 922 10 226, 665 227, 663 229, 392 230, 85 229, 815 229, 478 229, 104 Table 2. 20-year Augsep Oct Nov Dec Annual 1 184, 6 185, 2 185, 0 184, 5 184, 3 184, 0 2 189, 5 189, 9 190, 9 191, 0 190, 3 188, 9 3 196. 4 198, 8 199, 2 197, 6 196, 8 195, 3 4 203, 9 202, 9 201. 8 201, 5 201, 8 201, 6 5 207, 917 208, 490 208, 936 210. 177 210, 36 207, 342 6 219, 86 218, 783 216, 573 212, 425 210, 228 215, 303 7 215, 834 215, 969 216, 177 216, 330 215, 949 214, 537 8 218, 312 218, 439 218, 711 218, 803 219, 179 218, 56 9 226, 545 226, 889 226, 421 226, 230 225, 672 224, 939 10 230, 379 231, 407 231, 317 230, 221 229, 601 229, 594 Table 2, 21 Solution. This is a time series graph that matches the supplied data. The x-axis shows years from 2003 to 2012, and the y-axis shows the annual CPI. Figure 2, 10 Try it 2. 13 The following table is a portion of a data set from www.worldbank.org. Use the table to construct a time series graph for CO2 emissions for the United States. CO2 emissions year Ukraine United Kingdom United States 1 352, 259 540, 645, 681. 664 2 343, 121 540, 409 5, 790, 761 3 339, 29 541, 995, 826, 394 4 327, 797 542, 45 5 737, 615 5 328, 357 528, 631 5 828. 697 6 323, 657 522, 247 5 656, 839 7 272, 176 474, 579 5, 299 563 Table 2. 22 Uses of a time series graph. Time series graphs are important tools in various applications of statistics. When recording values of the same variable over an extended period of time, sometimes it is difficult to discern any trend or pattern. However, once the same data points are displayed graphically, some features jump out. Time series graphs make trends easy to spot. How not to lie with statistics. It is important to remember that the very reason we develop a variety of methods to present data is to develop insights into the subject of what the observations represent. We want to get a sense of the data. Are the observations all very much alike, or are they spread across a wide range of values? Are they bunched at one end of the spectrum, or are they distributed evenly, and so on? We are trying to get a visual picture of the numerical data. Shortly, we will develop formal mathematical measures of the data, but our visual graphical presentation can say much. It can, unfortunately, also say much that is distracting, confusing, and simply wrong in terms of the impression the visual leaves. Many years ago, Darrell Huff wrote the book How to Lie with Statistics. It has been through 25-plus printings and sold more than 1.5 million copies. His perspective was a harsh one and used many actual examples that were designed to mislead. He wanted to make people aware of such deception, but perhaps more importantly to educate so that others do not make the same errors inadvertently. Again, the goal is to enlighten with visuals that tell the story of the data. Pie charts have a number of common problems when used to convey the message of the data. Too many pieces of the pie overwhelm the reader. More than perhaps 5 or 6 categories ought to give an idea of the relative importance of each piece. This is, after all, the goal of a pie chart: what subset matters most relative to the others. If there are more components than this, then perhaps an alternative approach would be better, or perhaps some can be consolidated into an other category. Pie charts cannot show changes over time, although we see this attempted all too often. In federal, state, and city finance documents, pie charts are often presented to show the components of revenue available to the governing body for appropriation. Income tax, sales tax, motor vehicle taxes, and so on. In and of itself, this is interesting information and can be nicely done with a pie chart. The error occurs when 2 years are set side by side. Because the total revenues change year to year, but the size of the pie is fixed, no real information is provided, and the relative size of each piece of the pie cannot be meaningfully compared. Histograms can be very helpful in understanding the data. Properly presented, they can be a quick visual way to present probabilities of different categories by the simple visual of comparing relative areas in each category. Here the error, purposeful or not, is to vary the width of the categories. This of course makes comparison to the other categories impossible. It does embellish the importance of the category with the expanded width because it has a greater area inappropriately, and thus visually says that that category has a higher probability of occurrence. Time series graphs perhaps are the most abused. A plot of some variable across time should never be presented on axes that change part way across the page, either in the vertical or horizontal dimension. Perhaps the time frame is changed from years to months. Perhaps this is to save space or because monthly data was not available for early years. In either case, this confounds the presentation and destroys any value of the graph. If this is not done to purposefully confuse the reader, then it certainly is either lazy or sloppy work. Changing the units of measurement of the axis can smooth out a drop or accentuate one. If you want to show large changes, then measure the variable in small units, penny rather than thousands of dollars. And of course, to continue the fraud, be sure that the axis does not begin at 0, 0. If it begins at 0, 0, then it becomes apparent that the axis has been manipulated. Perhaps you have a client that is concerned with the volatility of the portfolio you manage. An easy way to present the data is to use long time periods on the time series graph. Use months or better, quarters rather than daily or weekly data. If that doesn't get the volatility down, then spread the time axis relative to the rate of return or portfolio valuation axis. If you want to show quick, dramatic growth, then shrink the time axis. Any positive growth will show visually high growth rates. Do note that if the growth is negative, then this trick will show the portfolio is collapsing at a dramatic rate. Again, the goal of descriptive statistics is to convey meaningful visuals that tell the story of the data. Purposeful manipulation is fraud and unethical at the worst, but even at its best, making these type of errors will lead to confusion on the part of the analysis. The common measures of location are quartiles and percentiles. Quartiles divide an ordered data set into 4 equal parts. The 3 quartiles of a data set are labeled as Q1, Q2, and Q3. About 1/4 of the data falls on or below the first quartile Q1. About 1/2 of the data falls on or below the second quartile Q2. About 3/4 of the data falls on or below the first quartile Q3. In the same way, percentiles divide a data set into 100 equal parts. To calculate quartiles and percentiles, the data must be ordered from smallest to largest. Quartiles divide ordered data into quarters. Percentiles divide ordered data into hundredths. To score in the 90th percentile of an exam does not mean necessarily that you received 90% on a test. It means that 90% of test scores are the same or less than your score, and 10% of the test scores are the same or greater than your test score. Percentiles are useful for comparing values. For this reason, universities and colleges use percentiles extensively. One instance in which colleges and universities use percentiles is when SAT results are used to determine a minimum testing score that will be used as an acceptance factor. For example, suppose Duke accepts SAT scores at or above the 75th percentile. That translates into a score of at least 1220. Percentiles are mostly used with very large populations. Therefore, if you were to say that 90% of the test scores are less, and not the same or less than your score, it would be acceptable because removing one particular data value is not significant. The median is a number that measures the center of the data. You can think of the median as the middle value, but it does not actually have to be one of the observed values. It is a number that separates ordered data into halves. Half the values are the same number or smaller than the median, and half the values are the same number or larger. For example, consider the following data. 1 11 5 6 7 2 4 8 9 10 6 8 8 3. 2 2 10 1 ordered from smallest to largest. 1 1 2 2 4 6 6 8 7 2 8 8 3 9 10 10. 11 5. Since there are 14 observations, the median is between the 7th value 6 8 and the 8th value 7 2. To find the median, add the two values together and divide by 2. 6 8 plus 7 2 equals 14 14 divided by 2 equals 7. The median is 7. Half of the values are smaller than 7 and half of the values are larger than 7. Quartiles are numbers that separate the data into quarters. Quartiles may or may not be part of the data. To find the quartiles, first find the median or second quartile. The first quartile, Q1, is the middle value of the lower half of the data, and the third quartile, Q3, is the middle value or median of the upper half of the data. To get the idea, consider the same data set: 1, 1, 2, 2, 4, 6, 6, 8, 7, 2, 8, 8, 3, 9, 10, 10, 11. 5. The median or second quartile is 7. The lower half of the data are 1, 1, 2, 2, 4, 6, 6, 8. The middle value of the lower half is 2. 1, 1, 2, 2, 4, 6, 6, 8. The number 2, which is part of the data, is the first quartile. 1/4 of the entire sets of values are the same as or less than 2, and 3/4 of the values are more than 2. The upper half of the data is 7, 2, 8, 8, 3, 9, 10, 10, 11, 5. The middle value of the upper half is 9. The third quartile, Q3, is 9. 3/4, 75% of the ordered data set are less than 9. 1/4, 25% of the ordered data set are greater than 9. The third quartile is part of the data set in this example. The interquartile range is a number that indicates the spread of the middle half, or the middle 50% of the data. It is the difference between the third quartile, Q3, and the first quartile, Q1. IQR equals Q3, Q1. The IQR can help to determine potential outliers. A value is suspected to be a potential outlier if it is less than 1/5 ICR below the first quartile or more than 1/5 ICR above the third quartile. Potential outliers always require further investigation. Note, a potential outlier is a data point that is significantly different from the other data points. These special data points may be errors or some kind of abnormality, or they may be a key to understanding the data. Example 2. 14. Problem for the following 13 real estate prices. Calculate the IQR and determine if any prices are potential outliers. Prices are in dollars: 389,950, 230,500, 158,000, 479,000, 639,000, 114,950, 5,500,000. 387,000, 659,000, 529,000, 575,000, 488,800. 1,095,000. Solution: order the data from smallest to largest. 114,950, 158,000, 230,500. 387,000, 389,950, 479,000, 488,800, 529,000. 575,000, 639,000, 659,000, 1,095,000. 500. 0 m equals 488. 800 q1 equals 230. 500 plus 387. 2 equals 308. 750 q3 equals 639. 0 plus 659. 2 equals 649. 0 IQR equals 649. 0s 308. 750 equals 340. 251. 5 ICR equals 15. 340. 250 equals 510,375 Q1. 5 ICR equals 308,750. 510,375 equals 201,625 Q3 plus 1. 5 ICR equals 649,000 plus 510,375 equals 1,159,375. No house price is less than 201,625. However, 5,500,000 is more than 1,159,375. Therefore, 5,500,000 is a potential outlier. Try it too. 14. For the following 11 salaries, calculate the IQR and determine if any salaries are outliers. The salaries are in dollars: $33,000, $64,500. $28,000, $54,000, $72,000, $68,500, $69,000, $42,000, $54,000. $120,000, $40,500. Example 215. Problem test scores for a college statistics class held during the day are 99, 56, 78, 55, 5. 32, 90, 80, 81, 56, 59, 45, 77, 84, 5, 84, 70, 72, 68, 32, 79. 90 test scores for a college statistics class held during the evening are 98, 78, 68, 83, 81, 89, 88, 76, 65, 45, 98, 90, 80. 84, 5, 85, 79, 78, 98, 90, 79, 81, 25. 5. For the two data sets, find the following: the interquartile range. Compare the two interquartile ranges. Any outliers in either set. Solution: the 5-number summary for the day and night classes is minimum Q1, median Q3, maximum day 32, 56, 74, 582, 599, night 25, 578, 81, 89, 98. Table 2. 23. The IQR for the day group is Q3, Q1 equals 82, 5, 56 equals 26. 5. The IQR for the night group is Q3, Q1 equals 89, 78 equals 11. The interquartile range, the spread or variability, for the day class is larger than the night class IQR. This suggests more variation will be found in the day class's class test scores. Day class outliers are found using the IQR times 1-5 rule. So Q1 IQR 1, 5 equals 56, 26, 5, 1. 5 equals 16, 25. Q3 plus IQR 1, 5 equals 82, 5 plus 26, 5, 1, 5 equals 122. 25. Since the minimum and maximum values for the day class are greater than 16, 25 and less than 122, 25 there are no outliers. Night class outliers are calculated as Q1 IQR 1, 5 equals 78, 11, 1, 5 equals 61, 5. Q3 plus IQR 1, 5 equals 89 plus 11, 1, 5 equals 105. 5. For this class, any test score less than 61, 5 is an outlier. Therefore, the scores of 45 and 25, 5 are outliers since no test score is greater than 105. 5. There is no upper end outlier. Try at 215. Find the interquartile range for the following two data sets and compare them. Test scores for class A: 69, 96, 81, 79, 65. 76, 83, 99, 89, 67, 90, 77, 85, 98, 66, 91, 77, 69, 80, 94. Test scores for Class B: 90, 72, 80, 92, 90, 97, 92, 75, 79, 68, 70, 80, 99, 95, 78, 73, 71, 68, 95, 100. Example 2. 1650 statistic students were asked how much sleep they get per school night, rounded to the nearest hour. The results were amount of sleep per school night hours, frequency, relative frequency, cumulative relative frequency 420. 40, 4550, 10 0, 14 6 7 0, 14 0, 28 7 12 0, 24 0, 52 8 14 0, 28 0, 89 7 0, 14 0, 94 10 3 0, 6 1. Table 2. 24. Find the 28th percentile. Notice the 0. 28 in the cumulative relative frequency column. 28% of 50 data values is 14 values. There are 14 values less than the 28th percentile. They include the 2 4s, the 5 5s, and the 7 6s. The 28th percentile is between the last 6 and the first 7. The 28th percentile is 6 5. Find the median. Look again at the cumulative relative frequency column and find 0. 52. The median is the 50th percentile or the second quartile. 50% of 50 is 25. There are 25 values less than the median. They include the 2 4s, the 5 5s, the 7 6s, and 11 of the 7s. The median or 50th percentile is between the 25th or 7 and 26th or 7 values. The median is 7. Find the third quartile. The third quartile is the same as the 75th percentile. You can eyeball this answer. If you look at the cumulative relative frequency column, you find 0. 52 and 0 80. When you have all the 4s, 5s, 6s, and 7s, you have 52% of the data. When you include all the 8s, you have 80% of the data. The 75th percentile then must be an 8. Another way to look at the problem is to find 75% of 50, which is 37.5, and round up to 38. The third quartile, Q3, is the 38th value, which is an 8. You can check this answer by counting the values. There are 37 values below the third quartile and 12 values above. Try it too. 1640 bus drivers were asked how many hours they spend each day running their routes, rounded to the nearest hour. Find the 65th percentile. Amount of time spent on route hours, frequency, relative frequency, cumulative relative frequency 212 0, 30 0, 33 14 0, 35 0, 65 4 10 0, 25 0, 95 4 0, 10 1. Table 2. 25. A formula for finding the KTH percentile. If you were to do a little research, you would find several formulas for calculating the KTH percentile. Here is one of them. K equals the KTH percentile. It may or may not be part of the data. I equals the index ranking or position of a data value. N equals the total number of data points or observations. Order the data from smallest to largest. Calculate letter 1D456 equals K100 letter 1D45B plus 1. If I is an integer, then the KTH percentile is the data value in the ith position in the ordered set of data. If I is not an integer, then round I up and round I down to the nearest integers. Average the two data values in these two positions in the ordered data set. This is easier to understand in an example. Example 2. 17 problem listed are 29 ages for Academy Award-winning Best Actors in order from smallest to largest. 18, 21, 22, 25, 26, 27, 29, 30, 31. 33, 36, 37, 41, 42, 47, 52, 55, 57, 58, 62, 64, 67, 69, 71, 72, 73, 74. 76, 77. Find the 70th percentile. Find the 83rd percentile. Try it too. 17 listed are 29 ages for Academy Award-winning Best Actors in order from smallest to largest. 18. 21, 22, 25, 26, 27, 29, 30, 31, 33, 36, 37, 41, 42, 47, 52, 55, 57, 58, 62. 64, 67, 69, 71, 72, 73, 74, 76. 77. Calculate the 20th percentile and the 55th percentile. Note you can calculate percentiles using calculators and computers. There are a variety of online calculators. Example 218 problem using table 224, find the 80th percentile. Find the 90th percentile, find the first quartile. What is another name for the first quartile? Solution using the data from the frequency table we have. Notice there are 50 data values in the table, so n equals 50. Calculate the index I as follows. I equals 80, 150 plus 1 equals 40. 8 since I equals 48, calculate the mean of the 40th and 41st data values. The 40th data value is 8, the 41st data value is 9, and the mean of these two data values is 8.5. Thus, the 80th percentile is 8.5. Calculate the index I as follows. I equals 90, 150 plus 1 equals 45. 9 since I equals 45, 9. Calculate the mean of the 45th and 46th data values. The 45th data value is 9, the 46th data value is 9, and the mean of these two data values is 9. Thus, the 90th percentile is 9. Another name for the first quartile is the 25th percentile. Proceed to calculate the 25th percentile. Calculate the index I as follows. I equals 25, 150 plus 1 equals 12. 75 since I equals 12. 75. Calculate the mean of the 12th and 13th data values. The 12th data value is 6, the 13th data value is 6, and the mean of these two data values is 6. Thus, the first quartile is 6. Try it too. 18. Refer to the table 225. Find the third quartile. What is another name for the third quartile? Collaborative exercise. Your instructor or a member of the class will ask everyone in class how many sweaters they own. Answer the following questions. How many students were surveyed? What kind of sampling did you do? Construct two different histograms. For each, starting value equals, ending value equals. Find the median, first quartile, and third quartile. Construct a table of the data to find the following. The 10th percentile, the 70th percentile, the percent of students who own less than 4 sweaters, a formula for finding the percentile of a value in a data set. Order the data from smallest to largest. X equals the number of data values counting from the bottom of the data list up to, but not including the data value for which you want to find the percentile. Y equals the number of data values equal to the data value for which you want to find the percentile. N equals the total number of data. Calculate X plus 0. 5 letter 1D466 N 100. Then round to the nearest integer. Example 2, 19 problem listed are 29 ages for Academy Award-winning Best Actors in order from smallest to largest. 18, 21, 22, 25, 26, 27, 29, 30, 31, 33, 36, 37, 41, 42, 47, 52, 55, 57, 58. 62, 64, 67, 69, 71, 72, 73, 74, 76, 77. Find the percentile for 58. Find the percentile for 25. Solution counting from the bottom of the list, there are 18 data values less than 58. There is one value of 58. X equals 18 and Y equals 1, X plus 0. 5 letter 1D466 N 100 equals 18 plus 0. 5 129 100 equals 63, 80. 58 is the 64th percentile. Counting from the bottom of the list, there are 3 data values less than 25. There is one value of 25, X equals 3 and Y equals 1, X plus 0. 5 letter 1D466 N 100 equals 3 plus 0. 5 129 100 equals 12. 7. 25 is the 12th percentile. Try it too. 19 listed are 30 ages for Academy Award-winning Best Actors in order from smallest to largest. 18, 21, 22, 25, 26, 27, 29, 30, 31, 31. 33, 36, 37, 41, 42, 47, 52, 55, 57, 58, 62, 64, 67, 69, 71, 72, 73, 74. 76, 77. Find the percentiles for 47 and 31. Interpreting percentiles, quartiles, and median, a percentile indicates the relative standing of a data value when data are sorted into numerical order from smallest to largest. Percentages of data values are less than or equal to the PTH percentile. For example, 15% of data values are less than or equal to the 15th percentile. Low percentiles always correspond to lower data values. High percentiles always correspond to higher data values. A percentile may or may not correspond to a value judgment about whether it is good or bad. The interpretation of whether a certain percentile is good or bad depends on the context of the situation to which the data applies. In some situations, a low percentile would be considered good. In other contexts, a high percentile might be considered good. In many situations, there is no value judgment that applies. Understanding how to interpret percentiles properly is important not only when describing data, but also when calculating probabilities in later chapters of this text. Note when writing the interpretation of a percentile in the context of the given data, the sentence should contain the following information. Information about the context of the situation being considered the data value of the variable that represents the percentile, the percent of individuals or items with data values below the percentile, the percent of individuals or items with data values above the percentile. Example 220 problem on a timed math test. The first quartile for time it took to finish the exam was 35 minutes. Interpret the first quartile in the context of this situation. Solution: 25% of students finished the exam in 35 minutes or less. 75% of students finished the exam in 35 minutes or more. A low percentile could be considered good, as finishing more quickly on a timed exam is desirable. If you take too long, you might not be able to finish. Try it too. 24. The 100-meter dash. The third quartile for times for finishing the race was 11.5 seconds. Interpret the third quartile in the context of the situation. Example 2. 21 problem on a 20-question math test. The 70th percentile for number of correct answers was 16. Interpret the 70th percentile in the context of this situation. Solution: 70% of students answered 16 or fewer questions correctly. 30% of students answered 16 or more questions correctly. A higher percentile could be considered good, as answering more questions correctly is desirable. Try it too. 21 on a 60-point written assignment. The 80th percentile for the number of points earned was 49. Interpret the 80th percentile in the context of this situation. Example 2. 22 problem at a community college. It was found that the 30th percentile of credit units that students are enrolled for is 7 units. Interpret the 30th percentile in the context of this situation. Solution: 30% of students are enrolled in 7 or fewer credit units. 70% of students are enrolled in 7 or more credit units. In this example, there is no good or bad value judgment associated with a higher or lower percentile. Students attend community college for varied reasons and needs, and their course load varies according to their needs. Try it too. 22 during a season, the 40th percentile for points scored per player in a game is 8. Interpret the 40th percentile in the context of this situation. Example 2. 23 Sharp Middle School is applying for a grant that will be used to add fitness equipment to the gym. The principal surveyed 15 anonymous students to determine how many minutes a day the students spend exercising. The results from the 15 anonymous students are shown. 0 minutes, 40 minutes, 60 minutes, 30 minutes. 60 minutes, 10 minutes, 45 minutes, 30 minutes, 300 minutes, 90 minutes, 30 minutes, 120 minutes, 60 minutes, 0 minutes, 20 minutes. Determine the following 5 values. Min equals 0, Q1 equals 20, med equals 40, Q3 equals 60, max equals 300. If you were the principal, would you be justified in purchasing new fitness equipment? Since 75% of the students exercise for 60 minutes or less daily, and since the IQR is 40 minutes, 60-20 equals 40, we know that half of the students surveyed exercise between 20 minutes and 60 minutes daily. This seems a reasonable amount of time spent exercising, so the principal would be justified in purchasing the new equipment. However, the principal needs to be careful. The value 300 appears to be a potential outlier. Q3 plus 1, 5 Iker equals 60 plus 1, 5, 40 equals 120. The value 300 is greater than 120, so it is a potential outlier. If we delete it and calculate the 5 values, we get the following values. min equals 0, q1 equals 20, q3 equals 60, max equals 120, we still have 75% of the students exercising for 60 minutes or less daily and half of the students exercising between 20 and 60 minutes a day. However, 15 students is a small sample and the principal should survey more students to be sure of his survey results. Try it too. 23. A college statistics instructor is investigating the amount of time students spend working on a final project in the course. The instructor would like students to spend approximately 3 to 4 hours as the typical amount of time to be spent on the project. The instructor collects data from a random sample of 10 students for the number of hours spent working on the final project. The results obtained are as follows: 2 hours, 3 hours, 5 hours, 3 hours, 4 hours, 4 hours, 3 hours, 11 hours, 3 hours, 2 hours. Determine the following 5 values: min q1, med q3, max. Should the instructor modify the final project or leave as is? The center of a data set is also a way of describing location. The two most widely used measures of the center of the data are the mean, average, and the median. To calculate the mean weight of 50 people, add the 50 weights together and divide by 50. Technically, this is the arithmetic mean. We will discuss the geometric mean later. To find the median weight of the 50 people, order the data and find the number that splits the data into two equal parts, meaning an equal number of observations on each side. The weight of 25 people are below this weight, and 25 people are heavier than this weight. The median is generally a better measure of the center when there are extreme values or outliers, because it is not affected by the precise numerical values of the outliers. The mean is the most common measure of the center. Note the words mean and average are often used interchangeably. The substitution of one word for the other is common practice. The technical term is arithmetic mean, and average is technically a center location. Formally, the arithmetic mean is called the first moment of the distribution by mathematicians. However, in practice among non-statisticians, average is commonly accepted for arithmetic mean. When each value in the data set is not unique, the mean can be calculated by multiplying each distinct value by its frequency and then dividing the sum by the total number of data values. The letter used to represent the sample mean is an X with a bar over it pronounced X bar. X, the Greek letter mu pronounced mu, represents the population mean. One of the requirements for the sample mean to be a good estimate of the population mean is for the sample taken to be truly random. To see that both ways of calculating the mean are the same, consider the sample 1, 1, 1, 2, 2. 3, 4, 4, 4, 4. 4x equals 1 plus 1 plus 1 plus 2 plus 2 plus 3 plus 4 plus 4 plus 4 plus 4 plus 4 11 equals 2. 7x equals 3, 1 plus 2, 2 plus 1, 3 plus 5, 4, 11 equals 2. 7 in the second calculation, the frequencies are 3, 2, 1, and 5. You can quickly find the location of the median by using the expression n plus 1, 2. The letter n is the total number of data values in the sample. If n is an odd number, the median is the middle value of the ordered data, ordered smallest to largest. If n is an even number, the median is equal to the two middle values added together and divided by 2 after the data has been ordered. For example, if the total number of data values is 97, then 2 equals 97 plus 1, 2 equals 49. The median is the 49th value in the ordered data. If the total number of data values is 100, then 2 equals 100 plus 1, 2 equals 50, 5. The median occurs midway between the 50th and 51st values. The location of the median and the value of the median are not the same. The uppercase letter M is often used to represent the median. The next example illustrates the location of the median and the value of the median. Example 224 problem: a hospital administrator keeps track of the ages. In years of patients visiting the emergency room over a 1-week period, data are sorted from smallest to largest. 3, 4, 8, 8. 10, 11, 12, 13, 14, 15, 15, 16, 16, 17, 17, 18, 21, 22, 22, 24, 24, 25, 26, 26, 27, 27. 29, 29, 31, 32, 33, 33, 34, 34, 35, 37, 40, 44, 44, 47. Calculate the mean and the median. Solution: the calculation for the mean is x equals 3 plus 4 plus 8, 2 plus 10 plus 11 plus 12 plus 13 plus 14 plus 15, 2 plus 16, 2 plus 35 plus 37 plus 40 plus 44, 2 plus 47, 40 equals 23. 6. To find the median m, first use the formula for the location. The location is 2 equals 40 plus 1, 2 equals 20. 5. Starting at the smallest value, the median is located between the 20th and 21st values, the two 24s, 3, 4. 8, 8, 10, 11, 12, 13, 14, 15, 15, 16, 16, 17, 17, 18, 21, 22, 22, 24, 24, 25, 26, 26, 27. 27, 29, 29, 31, 32, 33, 33, 34, 34, 35, 37, 40, 44, 44, 47. M equals 24 plus 24 2 equals 24. Try it 2. 24. The following data show the number of months patients typically wait on a transplant list before getting surgery. The data are ordered from smallest to largest. Calculate the mean and median. 3, 4, 5, 7, 7, 7, 7, 8, 8, 9, 9, 10, 10, 10, 10, 10, 11, 12, 12, 13, 14, 14, 15, 15. 17, 17, 18, 19, 19, 19, 21, 21, 22, 22, 23, 24, 24, 24, 24. Example 2. 25 problems. Suppose that in a small town of 50 people, one person earns $5 million per year and the other 49 each earn $30,000. Which is the better measure of the center, the mean or the median? Solution: x equals 5, 0, 0, 0, 0, 0, 0 plus 49, 30, 0, 0, 0. 50 equals 129, 400 m equals 30,000. There are 49 people who earn $30,000 and one person who earns $5 million. The median is a better measure of the center than the mean because 49 of the values are 30,000 and one is 5 million. The 5 million is an outlier. The 30,000 gives us a better sense of the middle of the data. Try it too. 25 in a sample of 60 households, one house is worth $2,500,000. $20 9 houses are worth $280,000, and all the others are worth $315,000. Which is the better measure of the center, the mean or the median? Another measure of the center is the mode. The mode is the most frequent value. There can be more than one mode in a data set as long as those values have the same frequency and that frequency is the highest. A data set with two modes is called bimodal. Example 2. 26 statistics exam scores for 20 students are as follows: 50, 53, 59, 59, 63, 63, 72, 72. 72, 72, 72, 76, 78, 81, 83, 84, 84, 84, 90, 93. Problem: find the mode. Solution: the most frequent score is 72, which occurs 5 times. Mode equals 72. Try it too. 26. The number of books checked out from the library from 25 students are as follows: 0, 0. 0, 1, 2, 3, 3, 4, 4, 5, 5, 7, 7, 7, 7, 8, 8, 8, 9, 10, 10, 11, 11, 12, 12. Find the mode. Example 2. 27 5 real estate exam scores are 430, 430, 480, 480, 495. The data set is bimodal because the scores 430 and 480 each occur twice. When is the mode the best measure of the center? Consider a weight loss program that advertises a mean weight loss of 6 pounds the first week of the program. The mode might indicate that most people lose 2 pounds the first week, making the program less appealing. Note the mode can be calculated for qualitative data as well as for quantitative data. For example, if the data set is red, 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 green, green, yellow, purple, black, blue, the mode is red. Try it too. 27 5 credit scores are 680, 680, 700, 720, 720. The data set is bimodal because the scores 680 and 720 each occur twice. Consider the annual earnings of workers at a factory. The mode is $25,000 and occurs 150 times out of 301. The median is $50,000 and the mean is $47,500. What would be the best measure of the center? Calculating the arithmetic mean of grouped frequency tables when only grouped data is available. You do not know the individual data values, we only know intervals and interval frequencies. Therefore, you cannot compute an exact mean for the data set. What we must do is estimate the actual mean by calculating the mean of a frequency table. A frequency table is a data representation in which grouped data is displayed along with the corresponding frequencies. To calculate the mean from a grouped frequency table, we can apply the basic definition of mean. Mean equals data sum number of data values. We simply need to modify the definition to fit within the restrictions of a frequency table. Since we do not know the individual data values, we can instead find the midpoint of each interval. The midpoint is lower boundary plus upper boundary 2. We can now modify the mean definition to be mean of frequency table equals sum sign letter 1 D453 letter 1 D45A sum sign letter 1 D453, where f equals the frequency of the interval and m equals the midpoint of the interval. Example 2, 28 problem: a frequency table displaying Professor Blount's last statistic test is shown. Find the best estimate of the class mean. Grade interval number of students 50 56, 5 1 56. 562, 5062, 568, 5468, 574, 5474, 580, 5280, 586, 5386, 592. 5492, 598, 51 Table 2, 26 Solution. Find the midpoints for all intervals. Grade interval midpoint 5056, 553, 2556, 562. 559, 562, 568, 565, 568, 574, 571, 574, 580, 577, 580, 586, 583. 586, 592, 589, 592, 598, 595, 5 Table 2, 27 Calculate the sum of the product of each interval frequency and midpoint. Sum letter 1d453 letter 1d45a 53. 25 1 plus 59, 5 0 plus 65, 5 4 plus 71, 5 4 plus 77, 5 2 plus 83, 5 3 plus 89, 5 4 plus 95, 5 1 equals 1460, 25 letter 1d707 equals sum sign letter 1d453 letter 1d45a sum sign letter 1d453 equals 1460, 2519 equals 76, 86 Try it 2. 28 A researcher conducted a study on the effect that playing video games has on memory recall. As part of the study, they compiled the following data. Hours teenagers spend on video games. Number of teenagers 03, 533, 57, 577, 511, 512, 11, 515, 5715, 519, 59 Table 2. 28 What is the best estimate for the mean number of hours spent playing video games? Formula for population mean letter 1d707 equals 1nn, letter 1d456 equals 1 formula for sample mean. X equals 1nn sum sign letter 1d456 equals 1 This unit is here to remind you of material that you once studied and said at the time, I am sure that I will never need this. Here are the formulas for a population mean and the sample mean. The Greek letter mu is the symbol for the population mean and X is the symbol for the sample mean. Both formulas have a mathematical symbol that tells us how to make the calculations. It is called sigma notation because the symbol is the Greek capital letter sigma, sigma. Like all mathematical symbols, it tells us what to do. Just as the plus sign tells us to add and the x tells us to multiply, these are called mathematical operators. The sigma symbol tells us to add a specific list of numbers. Let's say we have a sample of animals from the local animal shelter and we are interested in their average age. If we list each value or observation in a column, you can give each one an index number. The first number will be number 1 and the second number 2 and so on. Animal age 192138, 5410, 551068, 5712 88911095 Table 2. 29 Each observation represents a particular animal in the sample. Purr is animal number 1 and is a 9-year-old cat, Toto is animal number 2 and is a 1-year-old puppy and so on. To calculate the mean we are told by the formula to add up all these numbers, ages in this case, and then divide the sum by 10, the total number of animals in the sample. Animal number 1, the cat Purr, is designated as X1. Animal number 2, Toto, is designated as X2 and so on through Dundee, who is animal number 10 and is designated as X10. The I in the formula tells us which of the observations to add together. In this case it is X1 through X10, which is all of them. We know which ones to add by the indexing notation, the I equals 1 and the N or capital N for the population. For this example, the indexing notation would be I equals 1, and because it is a sample we use a small n on the top of the sigma, which would be 10. The standard deviation requires the same mathematical operator, and so it would be helpful to recall this knowledge from your past. The sum of the ages is found to be 78, and dividing by 10 gives us the sample mean age as 8 years. The mean, arithmetic, median, and mode are all measures of the center of the data, the average. They are all in their own way trying to measure the common point within the data, that which is normal. In the case of the arithmetic mean, this is solved by finding the value from which all points are equal linear distances. We can imagine that all the data values are combined through addition and then distributed back to each data point in equal amounts. The sum of all the values is what is redistributed in equal amounts such that the total sum remains the same. The geometric mean redistributes not the sum of the values, but the product of multiplying all the individual values, and then redistributing them in equal portions such that the total product remains the same. This can be seen from the formula for the geometric mean, tilde x. Pronounced x tilde, tilde x equals n letter 1d456 equals 1 equals letter 1d45b square root letter 1d465 1 letter 1d465 2 letter 1d465 letter 1d45b equals letter 1d465 1 letter 1d465 2 letter 1d465 letter 1d45b. 1n where letter 1d70b is another mathematical operator. That tells us to multiply all the xi numbers in the same way capital Greek sigma tells us to add all the xi numbers. Remember that a fractional exponent is calling for the nth root of the number, thus an exponent of 1/3 is the cube root of the number. The geometric mean answers the question, if all the quantities had the same value, what would that value have to be in order to achieve the same product? The geometric mean gets its name from the fact that when redistributed in this way, the sides form a geometric shape for which all sides have the same length. To see this, take the example of the numbers 10, 51, 2, and 8. The geometric mean is the product of multiplying these three numbers together, 4096, and taking the cube root because there are three numbers among which this product is to be distributed. Thus the geometric mean of these three numbers is 16. This describes a cube 16x16x16 and has a volume of 4096 units. The geometric mean is relevant in economics and finance for dealing with growth of markets, in investment, population, and other variables the growth in which there is an interest. Imagine that our box of 4096 units, perhaps dollars, is the value of an investment after 3 years, and that the investment returns in percents were the three numbers in our example. The geometric mean will provide us with the answer to the question, what is the average rate of return, 16%? The arithmetic mean of these three numbers is 23.6%. The reason for this difference, 16 versus 23.6, is that the arithmetic mean is additive and thus does not account for the interest on the interest, compound interest, embedded in the investment growth process. The same issue arises when asking for the average rate of growth of a population or sales or market penetration, etc., knowing the annual rates of growth. The formula for the geometric mean rate of return or any other growth rate is letter 1d45f letter 1d460 equals letter 1d4651 letter 1d4652 letter 1d465 letter 1d45b. 1n-1 manipulating the formula for the geometric mean can also provide a calculation of the average rate of growth between two periods knowing only the initial value a0 and the ending value n and the number of periods. The following formula provides this information. In a0, 1n equals tilde x. Finally, we note that the formula for the geometric mean requires that all numbers be positive greater than 0. The reason, of course, is that the root of a negative number is undefined for use outside of mathematical theory. There are ways to avoid this problem, however. In the case of rates of return and other simple growth problems, we can convert the negative values to meaningful positive equivalent values. Imagine that the annual returns for the past 3 years are plus 12%, minus 8%, and plus 2%. Using the decimal multiplier equivalents of 112, 0, 92, and 1. 2 allows us to compute a geometric mean of 167. Subtracting 1 from this value gives the geometric mean of plus 167% as a net rate of population growth or financial return. From this example, we can see that the geometric mean provides us with this formula for calculating the geometric mean rate of return for a series of annual rates of return. Letter 1d45f letter 1d460 equals tilde x minus 1, where letter 1d45f letter 1d460 is average rate of return, and tilde x is the geometric mean of the returns during some number of time periods. Note that the length of each time period must be the same. As a general rule, one should convert the percent values to its decimal equivalent multiplier. It is important to recognize that when dealing with percents, the geometric mean of percent values does not equal the geometric mean of the decimal multiplier equivalents, and it is the decimal multiplier equivalent geometric mean that is relevant. Consider the following data set: 4, 5, 6, 6, 6, 7, 7, 7, 7, 7, 7, 8, 8, 8, 9, 10. This data set can be represented by following histogram. Each interval has width 1, and each value is located in the middle of an interval. This histogram matches the supplied data. It consists of 7 adjacent bars with the x-axis split into intervals of 1 from 4 to 10. The highs of the bars peak in the middle and taper symmetrically to the right and left. Figure 2.11. The histogram in Figure 2.11 displays a symmetrical distribution of data. A distribution is symmetrical if a vertical line can be drawn at some point in the histogram, such that the shape to the left and the right of the vertical line are mirror images of each other. The mean, the median, and the mode are each 7 for these data. In a perfectly symmetrical distribution, the mean and the median are the same. This example has one mode, unimodal, and the mode is the same as the mean and median. In a symmetrical distribution that has two modes, bimodal, the two modes would be different from the mean and median. The histogram in Figure 2.12 for the data 4, 5, 6, 6, 6, 7, 7, 7, 7, 8 is not symmetrical. The right-hand side seems chopped off compared to the left side. A distribution of this type is called skewed to the left because it is pulled out to the left. We can formally measure the skewness of a distribution just as we can mathematically measure the center weight of the data or its general speedness. The mathematical formula for skewness is A3 equals sum letter 1 D465 letter 1 D456 minus X3 letter 1 D45B letter 1 D4603. The greater the deviation from 0 indicates a greater degree of skewness. If the skewness is negative, then the distribution is skewed left as in figure 212. A positive measure of skewness indicates right skewness such as figure 213. This histogram matches the supplied data. It consists of 5 adjacent bars with the x-axis split into intervals of 1 from 4 to 8. The peak is to the right and the heights of the bars taper down to the left. Figure 2:12 the mean is 6.3, the median is 6.5 and the mode is 7. Notice that the mean is less than the median and they are both less than the mode. The mean and the median both reflect the skewing, but the mean reflects it more so. The histogram for the data 6, 7, 7, 7, 7, 8, 8, 8, 9, 10 shown in figure 213 is also not symmetrical. It is skewed to the right. This histogram matches the supplied data. It consists of 5 adjacent bars with the x-axis split into intervals of 1 from 6 to 10. The peak is to the left and the heights of the bars taper down to the right. Figure 2:13 the mean is 7.7, the median is 7.5 and the mode is 7. Of the three statistics, the mean is the largest while the mode is the smallest. Again, the mean reflects the skewing the most. The mean is affected by outliers that do not influence the median. Therefore, when the distribution of data is skewed to the left, the mean is often less than the median. When the distribution is skewed to the right, the mean is often greater than the median. In symmetric distributions, we expect the mean and median to be approximately equal in value. This is an important connection between the shape of the distribution and the relationship of the mean and median. It is not, however, true for every data set. The most common exceptions occur in sets of discrete data. As with the mean, median, and mode, and as we will see shortly, the variance, there are mathematical formulas that give us precise measures of these characteristics of the distribution of the data. Again, looking at the formula for skewness, we see that this is a relationship between the mean of the data and the individual observations cubed. Letter 1 D44E3 equals sum letter 1 D465 letter 1 D456 minus X3 letter 1 D45B letter 1 D4603, where S is the sample standard deviation of the data, xi and X is the arithmetic mean and N is the sample size. Formally, the arithmetic mean is known as the first moment of the distribution. The second moment we will see is the variance, and skewness is the third moment. The variance measures the squared differences of the data from the mean, and skewness measures the cubed differences of the data from the mean. While a variance can never be a negative number, the measure of skewness can, and this is how we determine if the data are skewed right of left. The skewness for a normal distribution is 0, and any symmetric data should have skewness near 0. Negative values for the skewness indicate data that are skewed left, and positive values for the skewness indicate data that are skewed right. By skewed left, we mean that the left tail is long relative to the right tail. Similarly, skewed right means that the right tail is long relative to the left tail. The skewness characterizes the degree of asymmetry of a distribution around its mean. While the mean and standard deviation are dimensional quantities, this is why we will take the square root of the variance, that is, have the same units as the measured quantities xi. The skewness is conventionally defined in such a way as to make it non-dimensional. It is a pure number that characterizes only the shape of the distribution. A positive value of skewness signifies a distribution with an asymmetric tail extending out towards more positive x, and a negative value signifies a distribution whose tail extends out towards more negative x. A zero measure of skewness will indicate a symmetrical distribution. Skewness and symmetry become important when we discuss probability distributions in later chapters. An important characteristic of any set of data is the variation in the data. In some data sets, the data values are concentrated closely near the mean. In other data sets, the data values are more widely spread out from the mean. The most common measure of variation, or spread, is the standard deviation. The standard deviation is a number that measures how far data values are from their mean. The standard deviation provides a numerical measure of the overall amount of variation in a data set and can be used to determine whether a particular data value is close to or far from the mean. The standard deviation provides a measure of the overall variation in a data set. The standard deviation is always positive or zero. The standard deviation is small when the data are all concentrated close to the mean, exhibiting little variation or spread. The standard deviation is larger when the data values are more spread out from the mean, exhibiting more variation. Suppose that we are studying the amount of time customers wait in line at the checkout at supermarket A and supermarket B. The average wait time at both supermarkets is 5 minutes. At supermarket A, the standard deviation for the wait time is 2 minutes. At supermarket B, the standard deviation for the wait time is 4 minutes. Because supermarket B has a higher standard deviation, we know that there is more variation in the wait times at supermarket B overall. Wait times at supermarket B are more spread out from the average. Wait times at supermarket A are more concentrated near the average. Calculating the standard deviation if x is a number, then the difference x minus the mean is called its deviation. In a data set, there are as many deviations as there are items in the data set. The deviations are used to calculate the standard deviation. If the numbers belong to a population, in symbols a deviation is x mu. For sample data, in symbols a deviation is x. The procedure to calculate the standard deviation, depends on whether the numbers are the entire population or are data from a sample. The calculations are similar, but not identical. Therefore, the symbol used to represent the standard deviation depends on whether it is calculated from a population or a sample. The lowercase letter s represents the sample standard deviation and the Greek letter sigma lowercase, represents the population standard deviation. If the sample has the same characteristics as the population, then s should be a good estimate of sigma. To calculate the standard deviation, we need to calculate the variance first. The variance is the average of the squares of the deviations, the x values for a sample, or the x mu values for a population. The symbol sigma 2 represents the population variance. The population standard deviation sigma is the square root of the population variance. The symbol s2 represents the sample variance. The sample standard deviation s is the square root of the sample variance. You can think of the standard deviation as a special average of the deviations. Formally, the variance is the second moment of the distribution or the first moment around the mean. Remember that the mean is the first moment of the distribution. If the numbers come from a census of the entire population and not a sample, when we calculate the average of the squared deviations to find the variance, we divide by n, the number of items in the population. If the data are from a sample rather than a population, when we calculate the average of the squared deviations, we divide by n1, one less than the number of items in the sample. Formulas for the sample standard deviation letter 1d460 equals square letter 1d6f4, letter 1d465 minus, x2 letter 1d45b minus 1 or letter 1d460 equals square letter 1d6f4 letter 1d453, letter 1d465 minus, x2 letter 1d45b minus 1 or s equals square. In sum sign letter 1d456 equals 1 letter 1d465 2 minus letter 1d45b, x2 letter 1d45b minus 1 for the sample standard deviation. The denominator is n1, that is the sample size minus 1. Formulas for the population standard deviation letter 1d70 equals square root letter 1d6f4. Letter 1d465 minus letter 1d7072n or letter 1d70 equals square root letter 1d6f4 letter 1d453. Letter 1d465 letter 1d7072n or letter 1d70 equals square. In sum sign letter 1d456 equals 1x2i. Minus letter 1d7072 for the population standard deviation. The denominator is n, the number of items in the population. In these formulas, f represents the frequency with which a value appears. For example, if a value appears once, f is 1. If a value appears 3 times in the data set or population, f is 3. Two important observations concerning the variance and standard deviation. The deviations are measured from the mean and the deviations are squared. In principle, the deviations could be measured from any point, however, our interest is measurement from the center weight of the data. What is the normal or most usual value of the observation? Later, we will be trying to measure the unusualness of an observation or a sample mean, and thus we need a measure from the mean. The second observation is that the deviations are squared. This does two things. First, it makes the deviations all positive, and second, it changes the units of measurement from that of the mean and the original observations. If the data are weights, then the mean is measured in pounds, but the variance is measured in pounds squared. One reason to use the standard deviation is to return to the original units of measurement by taking the square root of the variance. Further, when the deviations are squared, it explodes their value. For example, a deviation of 10 from the mean when squared is 100, but a deviation of 100 from the mean is 10,000. What this does is place great weight on outliers when calculating the variance. Types of variability in samples when trying to study a population. A sample is often used, either for convenience or because it is not possible to access the entire population. Variability is the term used to describe the differences that may occur in these outcomes. Common types of variability include the following: Observational or measurement variability, natural variability, induced variability, sample variability. Here are some examples to describe each type of variability. Example 1. Measurement variability. Measurement variability occurs when there are differences in the instruments used to measure or in the people using those instruments. If we are gathering data on how long it takes for a ball to drop from a height by having students measure the time of the drop with a stopwatch, we may experience measurement variability if the two stopwatches used were made by different manufacturers. For example, one stopwatch measures to the nearest second, whereas the other one measures to the nearest tenth of a second. We also may experience measurement variability because two different people are gathering the data. Their reaction times in pressing the button on the stopwatch may differ, thus the outcomes will vary accordingly. The differences in outcomes may be affected by measurement variability. Example 2. Natural variability. Natural variability arises from the differences that naturally occur because members of a population differ from each other. For example, if we have two identical corn plants and we expose both plants to the same amount of water and sunlight, they may still grow at different rates simply because they are two different corn plants. The difference in outcomes may be explained by natural variability. Example 3. Induced variability. Induced variability is the counterpart to natural variability. This occurs because we have artificially induced an element of variation that, by definition, was not present naturally. For example, we assign people to two different groups to study memory, and we induce a variable in one group by limiting the amount of sleep they get. The difference in outcomes may be affected by induced variability. Example 4. Sample variability. Sample variability occurs when multiple random samples are taken from the same population. For example, if I conduct 4 surveys of 50 people randomly selected from a given population, the differences in outcomes may be affected by sample variability. Example 2. 29 in a 5th grade class, the teacher was interested in the average age and the sample standard deviation of the ages of the students. The following data are the ages for a sample of n equals 25th grade students. The ages are rounded to the nearest half year. 9, 9, 5, 9, 5, 10, 10, 10, 10, 10, 5, 10, 5, 10, 5, 10, 5, 11, 11, 11, 11, 11, 11, 11, 5, 11, 5, 11, 5. X equals 9 plus 9, 5 2 plus 10 4 plus 10, 5 4 plus 11 6 plus 11, 5 3 20 equals 10, 525 the average age is 10. 53 years rounded to 2 places. The variance may be calculated by using a table. Then the standard deviation is calculated by taking the square root of the variance. We will explain the parts of the table after calculating S data freak. Deviations 2 freak. Deviations 2 xf x 2f x 291910. 525 equals 1 525. When 525 2 equals 2 325,625 1 times 2. 325,625 equals 2 325,625 9. 529510. 525 equals 1. 25 10 25 2 equals 150,625 2 times 150,625 equals 2 101,250 10 4 10 10. 525 equals 0 525 0. 525 2 equals 0 275,625 4 times 0. 275,625 equals 110 25 10. 5 4 10 5 10. 525 equals 0 25 0. 0 25 2 equals 0 625 4 times 0 625 equals 0 25 11 6 11 10. 525 equals 0 475 0. 475 2 equals 0 225,625 6 times 0. 225,625 equals 135,375 11. 5 3 11. 5 10. 525 equals 0. 975, 0 975 2 equals 0 950,625 3 times, 0 950,625 equals 2. 851,875 the total is 9. 7375 table 2. 30 the sample variance S2 is equal to the sum of the last column 9. 7375 divided by the total number of data values minus 121, letter 1D4602 equals 9. 7375 20 minus 1 equals 0. 5125 the sample standard deviation S is equal to the square root of the sample variance, letter 1D460 equals square 0. 5125 equals 0. 715,891, which is rounded to 2 decimal places, S equals 0.72. Try it 2. 29 on a baseball team, the ages of each of the players are as follows. 21, 21, 22, 23, 24, 24, 25, 25, 28, 29, 29, 31, 32, 33, 33, 34, 35, 36. 36, 36, 36, 38, 38, 38, 40. Use your calculator or computer to find the mean and standard deviation. Then find the value that is 2 standard deviations above the mean. Explanation of the standard deviation calculation shown in the table. The deviations show how spread out the data are about the mean. The data value 11. 5 is farther from the mean than is the data value 11, which is indicated by the deviations 0. 97 and 0.47. A positive deviation occurs when the data value is greater than the mean, whereas a negative deviation occurs when the data value is less than the mean. The deviation is 1. 525 for the data value 9. If you add the deviations, the sum is always 0. For example, 229, there are n equals 20 deviations. So you cannot simply add the deviations to get the spread of the data. By squaring the deviations, you make them positive numbers and the sum will also be positive. The variance then is the average squared deviation. By squaring the deviations, we are placing an extreme penalty on observations that are far from the mean. These observations get greater weight in the calculations of the variance. We will see later on that the variance standard deviation plays the critical role in determining our conclusions in inferential statistics. We can begin now by using the standard deviation as a measure of unusualness. How did you do on the test? Terrific, 2 standard deviations above the mean. This, we will see, is an unusually good exam grade. The variance is a squared measure and does not have the same units as the data. Taking the square root solves the problem. The standard deviation measures the spread in the same units as the data. Notice that instead of dividing by n equals 20, the calculation divided by n1 equals 20, 1 equals 19 because the data is a sample. For the sample variance, we divide by the sample size minus 1 n1. Why not divide by n? The answer has to do with the population variance. The sample variance is an estimate of the population variance. This estimate requires us to use an estimate of the population mean rather than the actual population mean. Based on the theoretical mathematics that lies behind these calculations, dividing by n1 gives a better estimate of the population variance. The standard deviation, s or sigma, is either 0 or larger than 0. Describing the data with reference to the spread is called variability. The variability in data depends upon the method by which the outcomes are obtained. For example, by measuring or by random sampling. When the standard deviation is 0, there is no spread, that is, all the data values are equal to each other. The standard deviation is small when the data are all concentrated close to the mean, and is larger when the data values show more variation from the mean. When the standard deviation is a lot larger than 0, the data values are very spread out about the mean. Outliers can make S or sigma very large. Example 230 problem used the following data. First exam scores from Professor Dean's spring pre-calculus class: 33, 42, 49, 49, 53. 55, 55, 61, 63, 67, 68, 68, 69, 69, 72, 73, 74, 78, 80, 83, 88, 88, 88, 90. 92, 94, 94, 94, 94, 96. 100. Create a chart containing the data, frequencies, relative frequencies, and cumulative relative frequencies to 3 decimal places. Calculate the following to 1 decimal place. The sample mean, the sample standard deviation, the median, the first quartile, the third quartile, IQR, data frequency, relative frequency, cumulative relative frequency, 3310. 320, 324210, 320, 644920, 650, 129 5310, 320, 161 5520, 650, 226 6110, 320, 258 6310, 320, 29 6710, 320, 322 6820, 650, 387 6920, 650, 452 7210, 320, 480 47310, 320, 516 7410, 320, 548 7810, 320, 580 8010, 320, 612 8310, 320, 644 8830, 970, 741 9110, 320, 773 9210, 320, 805 9440, 129 934 9610, 320. 966 110, 32 998. Why isn't this value 1? Answer. Rounding table 231. Try it 2. 30. The following data show the different types of pet food stores in the area carry. 666677778999910101010 11 11 11 11 12 12 12 12 12 12. Calculate the sample mean and the sample standard deviation to one decimal place using a T83 plus or T84 calculator. Standard deviation of grouped frequency tables. Recall that for grouped data we do not know individual data values, so we cannot describe the typical value of the data with precision. In other words, we cannot find the exact mean, median, or mode. We can, however, determine the best estimate of the measures of center by finding the mean of the grouped data with the formula. Letter 1D440, letter 1D452, letter 1D44E, letter 1D45B, letter 1D45C, letter 1D453, letter 1D439, letter 1D45F. Letter 1D452, letter 1D45E, letter 1D462, letter 1D452, letter 1D45B, letter 1D450, letter 1D466. Sum sign letter 1D453, letter 1D45A, sum sign letter 1D453. Letter 1D453 equals interval frequencies, and M equals interval midpoints. Just as we could not find the exact mean, neither can we find the exact standard deviation. Remember that standard deviation describes numerically the expected deviation a data value has from the mean. In simple English, the standard deviation allows us to compare how unusual individual data is compared to the mean. Example 231. Find the standard deviation for the data in Table 232. Class frequency, F midpoint, MF letter 1D45A, letter 1D453, letter 1D45A minus X 2021111 equals 111 minus 6. 88 and 2 equals 34. 57 356464 equals 2464 minus 6. 88 and 2 equals 49. 77 6810 710 7 equals 7010 7 minus 6. 88 2 equals 0. 14 9 11 7 10 7 10 equals 77 10 minus 6. 88 and 2 equals 68. 14 12 14 0 13 0 13 equals 0 0 13 minus 6. 88 2 equals 0 n equals 24 x equals 165 24 equals 6. 88 s2 equals 152. 62 24 minus 1 equals 6. 64 table 232. For this data set we have the mean x equals 6. 88 and the standard deviation Sx equals 258. This means that a randomly selected data value would be expected to be 258 units from the mean. If we look at the first class, we see that the class midpoint is equal to 1. This is almost 3 standard deviations from the mean. While the formula for calculating the standard deviation is not complicated, letter 1D460, letter 1D465 equals square letter 1D6F4, letter 1D45A minus x 2 letter 1D453 letter 1D45B minus 1, where Sx equals sample standard deviation. X equals sample mean. The calculations are tedious. It is usually best to use technology when performing the calculations. Try at 231. Find the standard deviation for the data from the previous example class frequency. F0 2 1 3 5 6 6 8 10 9 11 7 12 14 0 15 17 2 Table 2. 33. Comparing values from different data sets. The standard deviation is useful when comparing data values that come from different data sets. If the data sets have different means and standard deviations, then comparing the data values directly can be misleading. For each data value x, calculate how many standard deviations away from its mean the value is. Use the formula x equals mean plus of stdev standard deviation. Solve for of stdvs. Letter 1D45C, letter 1D453, letter 1D446, letter 1D447, letter 1D437, letter 1D438, letter 1D449, letter 1D460 equals x mean standard deviation. Compare the results of this calculation. Of stdvs is often called a z-score. We can use the symbol z. In symbols, the formulas become sample x equals x plus zs letter 1D467 equals x minus xs population x equals letter 1D707 plus z sigma letter 1D467 equals x minus letter 1D707 letter 1D70 Table 2. 34 Example 232 Problem 2 Students, John and Ali from different high schools, wanted to find out who had the highest GPA when compared to his school. Which student had the highest GPA when compared to his school? Student GPA, school mean GPA, school standard deviation. John 2, 85,300. 7 Ali 77 80 10 Table 2. 35 Solution for each student. Determine how many standard deviations of STDEVs his GPA is away from the average for his school. Pay careful attention to signs when comparing and interpreting the answer. Letter 1D467 equals hash of stdevs equals value. Mean standard deviation equals letter 1D465 minus letter 1D707 letter 1D70E for John. Letter 1D467 equals hash letter 1D45C letter 1D453 letter 1D446 letter 1D447 letter 1D437 letter 1D438 letter 1D449 letter 1D460 equals 2. 85 minus 3. 007 equals minus 0. 21 for Ali, letter 1D467 equals hash letter 1D45C, letter 1D453, letter 1D446, letter 1D447, letter 1D437, letter 1D438, letter 1D449, letter 1D460 equals 77 minus 80 10 equals minus 0. 3 John has the better GPA when compared to his school because his GPA is 0. 21 standard deviations below his school's mean while Ali's GPA is 0. 3 standard deviations below his school's mean. John's z-score of 0.21 is higher than Ali's z-score of 0.3 for GPA. Higher values are better, so we conclude that John has the better GPA when compared to his school. Try it too. 32 swimmers, Angie and Bate from different teams, wanted to find out who had the fastest time for the 50-meter freestyle when compared to her team. Which swimmer had the fastest time when compared to her team? Swimmer time, seconds, team mean time, team standard deviation, Angie 26. 227, 20, 8 Bate 27, 330, 11, 4 Table 2. 36 The following lists give a few facts that provide a little more insight into what the standard deviation tells us about the distribution of the data. For any data set, no matter what the distribution of the data is, at least 75% of the data is within 2 standard deviations of the mean. At least 89% of the data is within 3 standard deviations of the mean. At least 95% of the data is within 5 standard deviations of the mean. This is known as Chebyshev's rule. For data having a normal distribution, which we will examine in great detail later, approximately 68% of the data is within 1 standard deviation of the mean. Approximately 95% of the data is within 2 standard deviations of the mean. More than 99% of the data is within 3 standard deviations of the mean. This is known as the empirical rule. It is important to note that this rule only applies when the shape of the distribution of the data is bell-shaped and symmetric. We will learn more about this when studying the normal or Gaussian probability distribution in later chapters. Coefficient of variation, another useful way to compare distributions besides simple comparisons of means or standard deviations, is to adjust for differences in the scale of the data being measured. Quite simply, a large variation in data with a large mean is different than the same variation in data with a small mean. To adjust for the scale of the underlying data, the coefficient of variation, CV, has been developed. Mathematically, letter 1D436, letter 1D449 equals SX asterisk 100 conditioned upon x not equal to 0. WHERE letter 1D460, ISTHESTONDA RDD via TIONOFTHEDA TND existhemian. We can see that this measures the variability of the underlying data as a percentage of the mean value, the center weight of the data set. This measure is useful in comparing risk where an adjustment is warranted because of differences in scale of 2 data sets. In effect, the scale is changed to common scale, percentage differences, and allows direct comparison of the 2 or more magnitudes of variation of different data sets.